So before we dive into this section, right, I just want to give you a quick heads up. There is a caveat around everything that we are doing with linear regressions. So the linear regressions have assumptions, okay? And if you see here, in addition to using the metrics like RMSE or adjusted R squared, you need to make sure that once you fit your model, all these assumptions are meeting, okay? So meeting. So here, the linear regression model makes the assumptions like linearity. So what is linearity? The relationship between the independent variable and the dependent variable is assumed to be linear. So in our case, in the model 2, we have used UDS and size because those two variables were having a linear relationship with the dependent variable price. Hence, it has been met with the linearity assumption. The next one is the homoscedasticity. For each value of the predictor, the variance of the return should be constant. So for example, so this is the error. So this is the error, right? When you plot the error in the chart, right, it should be something like this. It should be something like this. It should not be like this. So this is your, let's say this in the x-axis you have size and y-axis housing price, or let's say your error. Okay, this is your error. As the size increases, the square feet of the, let's say 500 square feet, 600 square feet, 800 square feet, 900. As the size of the houses increases, the error should be constant. Since the size is bigger, 900 square feet, the prediction values where, there is a significant difference between actual and predicted. And, there is an error. As the size increases, the error also, the increases. It should not be a pattern like this. So this is what I'm trying to say. Look here, the size is big, though the size is bigger, the error is just 1.1 only. Okay, here the size is smaller and 0.6, 0.4, 0.7. It's all very close by. Just because the size is bigger, if the error is something like 11.3, then it is something wrong here. Okay, there is something. As the size increases, the error should not also increase. It should be constant. Whether the size is small or bigger, it should be constant. Listen, here you have the 500 square feet and 600 square feet and 800 square feet. Here you have, let's say 900 square feet or 1000 square feet. So even for this 500 square feet, the difference between actual and predicted is somewhat, you are getting something like this. Okay. And this one, you are, let's say 500 square feet, 501, 502, 503, all these things, if you plot it, it is constant. Okay, it is constant, right? So 500 square, even for 500 square feet, sometimes you are getting the error like this, sometimes you are getting like this, sometimes you are getting like this. Even for 900 also you are getting something like this, something like that. But whereas in this case, 500 square feet is very less. It is not going beyond this. Okay, 600 also it is not going beyond. Suddenly for 800 and 900, as the size increases, the error also increases. It is violating the rule. Okay, this is called heteroscedasticity. Heteroscedasticity. There should not be any funnel shape. And instead, if you find something like this, this is called homoscedasticity. And if you go to the model here, we have a test available here to check whether we have homoscedasticity or not. So we have something called Durbin-Watson test. Instead of going by the visual, right? Instead of going by the visual, if you go by the test here, simple, this one will return the p-value. Durbin-Watson test, it will give you the p-value. If the p-value is less than alpha, you are going to reject the null hypothesis. And we are going to conclude that, when you, one second here, Lagrange multiplication, okay. Bruce-Pagan test, okay. Bruce-Pagan, Durbin-Watson test strategy is this one. One second, let me just. I don't want to make mistake. For the sake of confirmation, I just go here for model evaluation and model output. Look here. Test for Durbin-Watson test is for homoscedasticity. Okay, and you have, okay, so this is for homoscedasticity. You use Durbin-Watson test. This test will return the it will return the test statistics. See, in this case, test statistics is 2.04. And also with this, you can get the p-value also. Okay, you can get the p-value also. And okay, test, right? So test dot p-value. If you type the test dot p-value, you'll get the p-value. If the p-value is less than alpha, you're going to reject the null hypothesis. Okay. And so what is the null hypothesis? Here, there is no homoscedasticity. And since you are rejecting it, and you are going to conclude there is a homoscedasticity. The next one is multicollinearity. So variance inflation factor. In the interview, they asked one of my students, what is variance inflation factor? So he had asked him the next assumption is so using Durbin-Watson test, also you can find out if you have any heteroscedasticity, if you have a pattern, error pattern is like a funnel kind of thing, right? So that is what. Okay, so we use heteroscedasticity. We have something else called Bruce-Pagan. Okay, here no heteroscedasticity, and we are going to reject this, and we are going to conclude that is the one. And here it is Bruce-Pagan test. No, it is something like this. We have seen this one, right? Durbin-Watson. We use Durbin-Watson test. Okay, and third one is multicollinearity. What is multicollinearity? The correlation between the independent variables. Like in our case, the Park and MIC, these two independent variable itself has a correlation. It should not have correlation. Okay, since these two independent variable itself have a correlation, we call this a multicollinearity. How do you find out the multicollinearity? Using the correlation matrix also we can find out. And we have, we have something called variance inflation factor that is available, using which also we can find out. So when I pass the X values, the independent values, right, independent variables values, it shows something like this. If any value, print VIF. So this is the one in yourself. This is correlation value. Ignore this and print VIF. This variable inflation factor for whichever variable the value is very high. Let's if the value, the variable inflation value is greater than 10, then there is a multicollinearity. For look here, 215, 216. This is for Park and MIC. These two variables, the variance in factor value was more than 10. Hence, we can conclude with this also that there exists a multicollinearity. So how do you address the multicollinearity? That is the next question. Simply remove the variables that have collinear. We cannot blindly remove these two variables. What you can do is you can keep Park variable in this thing, and then you just check of these two variables, keep only one variable. Okay, remove one the other variable, and then you just check your model RMSE, and then what you do is in the next model you remove this variable and then keep this. See, I just write it here. See, we have the model, right? This is my model name. So in this case, what I do is the price is the dependent variable. Tilde, you have size plus UDS plus Park and MISC. So as per our correlation matrix, these two variables are, having a correlation, but these two variables are not correlated with my housing price. Hence we dropped it. Let us assume that these two variables also having a correlation with my price variable. Then it is fine. We need to retain it. But these two variables are having correlation, this target variable, and also it has a correlation between these two variables. Then something wrong. In that case, how do I address the multicollinearity? In that case, what we need to do is size plus UDS plus Park to create another model, model 1. Okay, and price and tilde, and you create another model, model 2, and price size plus UDS plus MISC. Okay, these two variables, you keep only one variable, knock out the other variable in one model, and in another model, you knock out this variable and keep this variable, and just check what is the RMSE for this, what is the RMSE for this, what is the RMSE for this. Okay, whichever model has lesser RMSE, then you can go for that. But you might be asking this question, sir, in this case, we have oddly 4 features are there. If I have 10 features, this, I have something else called lights, number of lights, pool, swimming pool, likewise, so many things are there. So all these variables are, these two variables are correlated and these two variables are correlated. In that case, how do I, so I'll end up creating so many models. So we have something called principal component analysis. Principal component analysis. This is another machine learning model using which we can address the multicollinearity. At this moment, you just say how to find out the multicollinearity. So using VIF function, variance inflation function, we can find the multicollinearity. If any variable which has more than 10 value if any variable which has the variance inflation factor value is greater than 10, then those variables are having multicollinearity. So to address that, we can better go for principal component analysis algorithm. So we have another way we can, if the number of independent variables are like this, you can do it this way. You can follow this approach to address this issue. See, if something is there, how do you find out, right? If something like, somebody is having a fever, how do you find out? Finding out is not sufficient. How do you cure it? How do you control it, right? So the same thing is applicable here. So how do you find out the multicollinearity? So your model should not have multicollinearity. Make sure that you're not having if it has multicollinearity, how do we address that? So approach one is this one. If the number of independent variables are more, and if the correlation, if more number of independent variables are correlated, better you can go for principal component analysis. Apart from this, we have something else called ridge regression. This is a regularization technique. Okay, ridge regression is another algorithm, machine learning algorithm, using which you can, this algorithm, what it does is it automatically addresses the multicollinearity. Okay, the ridge regression. Okay, so there are three approaches. One is like this. This is time-taking one. You say the best one is the PCA, and the third one is ridge regression. Okay, ridge regression also has some disadvantage. Okay, the PCA is the best one. That PCA will explain it later. Okay, it takes more time to explain it. Okay, so that's what I mentioned. Using correlation matrix also we can find out the multicollinearity, and using variance inflation factor also we can find it. Once you find out what is the solution, that is what, remove one of the correlated variables or combine the correlated variables. Best option is PCA. You can use the principal component analysis. Okay. And next one is autocorrelation. Error terms should be independent. So this error and this error should be independent. There should not be any correlation between this error and this error, this and this error. It should be, error should be independent. It is pretty simple and straightforward. For that, to find out the autocorrelation, use something called Bruce-Pagan test. We use something called Bruce-Pagan test. Using Bruce-Pagan test, we can find out you can conduct the Bruce-Pagan test. If the Bruce-Pagan test also returns p-value. If the p-value is less than alpha, you are going to reject the null hypothesis. Okay, and next one is normality of residuals. When you plot all these errors, right, it should be something like straight line. Okay, it should be like normal. Okay, gives us it should be, the error should be normal. Normality of errors. Because the normality of errors or residuals, it's all same. So hope you understood all these 5 different assumptions. In addition to validating the model using adjusted R squared or root mean squared error, you need to validate the assumptions also. If all your assumptions met, then your model is good. Okay. And if you have multicollinearity, and if you address, let's say your error is less after removing the variables that are not much helpful. In some cases, you would have included the variables, independent variables that have collinearity, right? So after addressing the collinearity also, your model accuracy can go high. In the sense the error can go down. Okay. So in addition to these assumptions, we need to check, do we have any unusual or influential data in our data set? We have something called outliers and leverage and influence. We need to check this one also in the model. Okay. So we know what is an outlier. Okay. So whenever you try to fit a line over data points, you can come across either an influential point or an outlier. Okay, if the model is underestimating the response value, then it will be indicated with positive residual. On the other hand, if the model is overestimating the response value, then it will be indicated by negative residual or the error. Okay. So for example, so we have something called influence. Influence can be thought of as the product of leverage and outlierness. Okay. Removing the observations changes the estimate of the thing. So instead of going through this definition, if you look at this visual, you will be able to understand very clearly. For example, I have an outlier, something like this, okay, here. So all the values are somewhat, for example, there are two lines here. You just assume that you don't have this value here, okay? So I red color value, okay? So this is nothing but the actual value. Since it is far off from this data set, it is an outlier, and also it is an influential point. Just because of this, what happens? This line got dragged, right? So in order to make sure that the values are closer to all these values, right? So including this value, this line should be somewhat closer, right? To all the values, including this one. Because of the presence of the outlier, this line goes down. Okay, if you remove this record or data, right, from your data set, what will happen is, this line will go up here, and then it is nicely fitted with all the other values. Just because one outlier, this line got dragged from here to here, right? And since this line got dragged from here to here, because to take care of this data also, right, the line will get influenced because of this, the outlier, and this is called influential point. Got it? What if I have, instead of having the value here, if I have the value here somewhere here, the same thing, right? So this line gets pulled from here to here, right? So now the line, got drawn here because of this outlier. This is also an influential point. If you have the value here, some outlier here, even this one also influencing your line, best fit line. Even this value, this outlier also influencing your best fit line. Instead of drawing the best fit line somewhere here, right, it is pulling this towards this one, and this all called the influential point. Okay, I have another scenario. After I fitted the model, right, so if I plot it, I'm getting something like this. But one extreme value is there. This value is far off from this. You know what is outlier, right? Observe the unusually very high value, right? Something like that. Okay, unusually very low value, unusually very high value is called outlier. But in this case, we have an outlier, but this outlier is present on the best fit line itself. Hence, we cannot call it as an influential point. So with this, what we are understanding is not all the outliers are, influential point. Got it? Is this an influential point? No, that's what I am trying to say. Okay, you have another data value here, right? So like this, you have something here. So can someone tell me, is this an influential point, or is this an outlier? It is not an outlier. It is an influential point. Okay, so this value is not too far off from these values, but still this value can have an influence on this trend. Slightly it can, it can pull this line little bit up, right? So in this case, though it is not an outlier, it is an influential point. Okay, it has an influence on the straight line, but in this case, though we have an outlier, it is not an influential point in this case. But in this case, we have outlier. The outliers are influential in that case. And next scenario is, okay, this is an outlier. Yes, right. It is an outlier and it is an influential point. Just because this value is far off from this here, right? Obviously, this line will get influenced. To take care of this value also, the line, the best fit line will have to draw somewhere here, right? So because of one value, so that's why the linear regression algorithm is sensitive to outlier, but not all the situations the outliers are influential. That is what we are going to conclude with this one. Okay, so why should I care about influential point, right? So the influential point, if you remove the influential point, right, it can significantly change the fit. With that itself, we can understand these are the records or having, these are the records have outliers in it. By removing the outlier, I can improve my accuracy, model accuracy. Okay, Cook's distance is commonly used influence measure. We have something called Cook distance, using which we can identify the influential point. So here I have used the R package. We have directly Cook's dot distance function is available. And also when you plot it, look here in the Cook's distance, right? So we can see that anything above the mean, so if the values are 3 times more than the mean value, those are the influential point. This is one simple rule of thumb. And if you look at this chart here, right, influence point, leverage and error, right? So in the influence point, what the values are bigger one, right? So or 130 or far off from this one. So the record number 130 and 101, 16, these are all the influential point. If you remove these observations or the records from your data, it can significantly change the fit. That means who knows, the error may go down further. Okay, so using Cook distance also we can find out, right? So, and this is the R thing. So now you understood what is Cook distance. Using Cook distance, we can find out the influential observation. Now you understood what is influential observation, all the things, right? Okay, fine. We are all set. Okay, so we are done with the linear regression assumption. So hope you understood with this, right? So the 5 assumptions, you need to remember all these 5 assumptions. So linearity, and there should be homoscedasticity, and the next one is the residual linearity in the residuals. Okay, residual should be linear, and the other one is no autocorrelation, no multicollinearity. Okay, so you need to keep this in mind. In case of multicollinearity, how do you deal with this? You need to know all the things. Okay.